Hello, everyone. Welcome to the Knowmads podcast. I'm your co host Prachi.
And I'm your co-host Bhavya.
Modern physics rests on two foundational frameworks that describe our universe at different scales. The first is General Relativity, which is the Einstein's theory of gravity that describes gravity not as a force but as the curvature of spacetime. At the microscopic scale, we have quantum mechanics, which describes the probabilistic nature of particles like electrons and photons. Quantum mechanics also laid the foundation for quantum field theory, where particles are no longer seen as standalone objects but as excitations of quantum fields that permeate spacetime. Individually, both theories aren't just theoretically robust but also experimentally validated. However, combining them isn't as easy as it sounds. When we try to apply quantum principles to spacetime itself, the equations break down. One of the most ambitious and mathematically rich attempts to reconcile these two frameworks is string theory. In string theory, the point-like particles are replaced by tiny vibrating strings, and different vibrational modes correspond to different particles. Even though string theory comes with its own challenges, like the need to compactify extra dimensions, it remains one of the most compelling candidates for a unified theory of nature. One of its greatest successes lies in the discovery of dualities, which connect seemingly unrelated theories. Among the most powerful of these is the ADS CFT Correspondence, or gauge gravity duality, which proposes an equivalence between a theory of gravity in higher dimensional spacetime and a quantum field theory without gravity on its lower dimensional boundary. Our guest today is Professor Andreas Karch, a theoretical physicist at the University of Texas at Austin, who has played a key role in shaping our understanding of gauge gravity duality and has made significant contributions to string theory. If you're someone curious about why we need to quantize gravity, eager to unpack the ideas behind string theory, or simply someone who's excited to explore the frontiers of fundamental physics, you're in for a treat. Before we start this episode, there's something I'd like to mention. We went all the way from Houston to Austin to record this episode in his office. But because tech can be sneaky sometimes, we ended up losing our video footage, mine and Bhavya's. Thankfully, Andreas's camera kept rolling. It was incredibly heartbreaking, but we didn't want to lose this episode, so we got creative. If you're watching this on YouTube, the visuals you'll see for the hosts are AI-generated avatars. The audio is 100% real. We have worked very hard to create a compelling visual experience, and we hope you like it. And like all our episodes, this conversation is raw, unedited, and without any cuts. With that out of the way, let's go.
Professor Andreas Karch, welcome to the Knowmads podcast.
Thanks for having me.
So, there's rising concerns about progress in theoretical physics, especially in the high energy community. I've personally come across people telling me that the field is doomed, apparently. So, apart from many other puzzles in the world of physics, and some of which we will talk about in the episode, I want to start by asking you particularly why quantizing gravity is a natural thing to do, and are these concerns genuine or superficial in the community?
Okay, these were two questions. Let me start with why quantizing gravity is important. I think we've known this for like many decades that the two pillars of modern physics, quantum mechanics and gravity, don't go together, right? One governs the very small, one governs the very big. So it's not often that the two actually talk to each other, right? It's sort of deep inside black holes very early in the universe, right? It's part of the problem why it's so hard to actually settle these questions. But these are two pillars of modern physics, and they're inconsistent with each other as they stand. So it's sort of physics can't possibly be complete if like the two main ingredients we have in order to understand the world around us do not fit with each other into one mathematical framework. I mean, we do know one framework where they do fit, which is string theory, but right? It's not obvious that that's the only one. It's not the only one people found after decades of looking. So that looks pretty good. But then we don't know whether string theory is actually the solution for like the problem of quantum gravity in the world around us. But I would insist that no, as physicists, we can't stop looking until we found a way of making quantum mechanics and and gravity consistent with each other, given that they describe sort of everything around us quite well. When one or the other is applicable, but not when they're both needed.
Right.
And then the other question was like about the progress in theoretical physics, right? Sort of, it's true that things are slower than they used to be, but it's also because the problems are hard, right? Physics is a very mature subject. Physics is like has been around for a very long time, and we do understand the world around us really, really well, right? It's these corners where like the basic laws of physics describe sort of everything except for what's going on deep inside the black hole, right? The very early universe. There we have some true inconsistencies, but to add to physics, it's kind of got harder because we're already pretty good, but that doesn't mean there's no progress, right? Sort of, I think we do make quite a bit of progress at the basic level in terms of understanding the structures, the mathematical structures in quantum field theory better, and that has sort of applications to other areas of physics, right? That sort of progress that's being made in high energy physics on understanding quantum field theory better has certainly crosstalk with condensed matter physics. And I wouldn't say that we teach them, right? It's sort of, but they like talking to us because we can learn from each other,
right?
Because we both use quantum field theory as a tool. There's a lot of impact of high energy physics on mathematics, where like many of the structures that are very natural in physics can help mathematicians in their quests because they're good at proving things, but physics is good at coming up with things that they should prove, right? Because physics is sort of this amazing structure that sort of fits together like really nicely and sometimes requires sort of mathematical facts that are really surprising. And there's sort of, thinking in this very basic physics kind of does motivate new places where we could look for new physics, right? It's sort of, many experiments are trying to push the frontiers of physics. They kind of have to have some idea what they're looking for, right? These are very expensive experiments. You want to have sort of a motivation of where's a reasonable place to look. And I think developing theories helps you get some sort of sense where there might be something new to look. You might say, well, so far nobody has found anything beyond the standard model. That wouldn't be quite right? Neutrino masses are definitely beyond the standard model physics, right? They're kind of not super surprising, maybe. They were quite surprising when I was a grad student, but these days people kind of accepted that they're there. And one can augment the standard model quite easy to account for neutrino masses, but there are many ways to augment the standard model to include them. So dark matter is beyond the standard model physics. So we know there's some out there, but it's true that these problems haven't changed a lot for the last 10, 20 years, but don't think that means there's no progress. It's just kind of slow progress. And if we completely give up, then there will certainly. It's the only way to make sure there will be no more progress is to just say we should stop working on physics.
Interesting. So let's talk about string theory now. I mean, even though it's not the candidate for quantum gravity, it's obviously the most talked about candidate.
Yeah, I think it's the only one that's actually delivered on giving me a consistent quantum theory of gravity.
Exactly.
Right? It's, we don't know whether it's the quantum theory of gravity of the world around us, but it's a consistent framework which has both gravity and quantum mechanics in there and gives me finite answers for any process you want to calculate within string theory. So
that's precisely what I want to know. So when we talk about string theory, we talk about how we should look at the fundamental particles as vibrating strings, but obviously it's much more nuanced than that. So how would you describe what is string theory?
I mean, it is this basic idea, right? That sort of the fundamental objects are not like perfect points, but perfect lines. And that avoided a lot of problems. You can sort of intuitively understand this, right? What makes quantum gravity hard, you can already understand sort of at the classical level, where if you look at the classical gravitational force law, that is sort of inverse square law. So gravitational forces get sort of bigger and bigger and bigger as 2 points approach each other, and formally get infinitely large if 2 points are like on top of each other. And so if the fundamental building blocks of nature are sort of perfect points, you have like in gravity you have these divergences built in. It's the same in electromagnetism, but in quantum mechanics we solved the ones with electromagnetism, but just by sort of dimension counting you can see in gravity this doesn't work. So if you just do dimensional analysis, unit counting, right? It's easy to check that in gravity just including quantum effects is not good enough to resolve this infinity. Now you might wonder, well, what if my fundamental particle isn't the point, but it's sort of something extended? But then it's like turtles all the way down, right? If my basic particle is extended, you have to, so what is it made of, right? What is its structure? Sort of, you're clearly not done explaining the microscopic physics of the world if you always have to keep on asking what is it made of. And the line somehow ended up being the perfect solution, where it sort of has no thickness, right? These fundamental strings, they still don't have any internal structure. But by the virtue of being a line rather than a point, they avoid these infinities that you get when you kind of calculate the gravitational attraction between two lines, because they never really hit each other exactly. And afterwards, you can sort of rationalize why this happened, but people weren't looking for this, right? When they discovered strings, they discovered string theory as a theory of the strong interactions. They thought maybe nuclei are really just made out of strings, and then they kind of always found this annoying massless spin 2 particle in there, and then only later realized, well, what we really found was a theory of quantum gravity, and then it works perfectly. There's gravitons in there, you can scatter them, you get finite answers. You live in 10 dimensions, but other than that, it's sort of a perfect theory of quantum gravity. It gives finite answers, which is very unique to string theory, that you can actually make sense of it on the quantum mechanical level. You can ask what happens if you scatter two gravitons off each other, and you get an answer that's just, it's not infinity. It doesn't violate probability conservation. It's just, it's exactly what the doctor ordered.
Right. Yeah, so this automatic consequence, which gravity was when you do string theory, is I think what took it off, and that's why the community sort of adapted it instantly.
Right.
Is that right?
Right. I mean, because I think there's sort of the way I like to tell the story. Like in the early days, people sort of quantizing gravity seems so hard, right? If we find any way of doing it that's truly going to be so unique, this is going to be like the theory of everything right there in front of our nose. And then they find string theory, and they thought, okay, we got it. And then only later did they realize it wasn't as unique as they thought, right? Quantizing gravity ended up being some level easier than they thought. There's not just like one way of doing it within string theory. There are many ways of doing it within string theory. It's all about these extra dimensions, right? We are up in 10 dimensions. That's not really a problem, because we can sort of hide 6 dimensions in some really nice small internal space. But there's like a lot of ways of doing that, and then you suddenly end up with, from the 40 point of view, so if you want to describe our world, you end up with like an infinite number of options, and sort of that's where we are right now, right? So it's not like string theory doesn't work, but it doesn't give me a unique answer for what the world should be. So it's kind of hard to check whether it's actually right. Is the world around us, is this described by string theory or not? It's kind of, it seems to be possible to accommodate it within string theory, but that's not really. No, I mean, that's great. I think that's a great thing that string theory is like a consistency of quantum gravity, which seems to be in principle consistent with the world around us. But you want to do better than that, right? You want to find something that string theory predicts about the world that you wouldn't have known otherwise, that we didn't know before by just studying quantum field theory and classical gravity.
That makes sense. Absolutely. So yeah, we'll keep digging into this. Another game-changing idea, which it has been around for about a century now, is the idea of dualities, and it's the idea that there's a robust equivalence between seemingly different physical systems. So my question to you is that with the onset of string theory, of course, these dualities sort of gained their popularity, and everyone was talking about it. And a remarkable duality that led to that came out of string theory was this AdS-CFT duality, or the gauge gravity duality. And we will be talking about AdS-CFT in much more detail in a while. But can you start by explaining what exactly is duality? What does it mean for theories to be dual?
I think you already explained it, right? It's sort of, there's like two seemingly different looking theories which in the end describe the same physics, right? And by different looking theories, I mean sort of it's the degrees of freedom you write down in terms of which you formulate your theory. Maybe one example would even be QCD. That's maybe so the theory of the strong interactions, where you can write down the theory in terms of quarks and gluons. That description is theoretically very appealing because it's sort of a complete description. You can calculate things in sort of using the standard tools of quantum field theory, perturbation theory. But there's another description where you try to write down the theory of the strong interaction in terms of like nuclei and mesons. That's sort of what people did in the old day. That's a good description at low energies. You can use that description. And those two are completely equivalent, right? you're using different degrees of freedoms as your basic input. But in the end, the physics you're describing is exactly the same. If you ask yourself, what would I actually measure in my lab, you get the same answers. And in the case of the strong interactions, right, one description in terms of mesons and baryons, in terms of nuclei and sort of some other particles that can exchange with each other.
Right.
Those degrees of freedom are very natural because those are the degrees of freedom that we're seeing, right? If you want to know what nuclear physics is all about, you think it's about nuclei, right? Because that's right. That's what the table is made of. That's what we see in the world around us. So it has advantages. It directly maps to what I would call the low energy physics, the observable universe. But theoretically, it's harder to work with, right? It's not a complete description. It has sort of difficulties at high energies. Whereas the theory of quarks and gluons, that's the actual sort of, I would say, underlying description. But right, that's sort of counterintuitive because the degrees of freedom you're seeing are not the degrees of freedom you put in terms of which you formulate your theory, right? You write down a theory in terms of quarks and gluons, and then you don't see quarks and gluons. You end up seeing protons and neutrons.
Right.
So, but I would think that's sort of already some version of a duality. And we discovered, there are many, many more of this, where you kind of have like two different microscopic sets of degrees of freedom. They can look very, very different, but they end up describing the same experimentally observable phenomena, either in like real theories in the real world or in sort of fictitious universes that you can only realize on a piece of paper, where you write like two different theories, different microscopic degrees of freedom that in the end give me the same observable phenomenon. And where string theory comes in, that string theory is like, it's a machine that produces lots of these dualities for you. You kind of look at these like, within strings, you look at some extended objects and you ask yourself, how do I describe these extended objects? And then you find there are two different ways of looking at it, and then that produces a duality for you. The ADS-CFT, the one you mentioned, is exactly obtained this way. You have like these extended objects, like we call them branes in general, it's like generalization of the word membrane. Sort of a membrane I would now call like a two-brane because it's like two spatial dimensions, and we can, if you live in 10 dimensions, you can have extended objects with like 5 spatial dimensions or 4 spatial dimensions. And so you take a 3-brane, so something which has like 3 space, 1 time dimension, and you look at it and you can say, well, this is an object that has energy, so by Einstein's general relativity should somehow bend space. And so if I look at it this way, it's some curved space-time corresponding to this D3-brane. But I can also think of these branes in string theory. I can describe them by the strings that end on it. And that gives me a very different description. Would say this is kind of looks like it's described by some sort of gauge theory. And then you say, well, I'm describing one and the same object. It should either be a gauge theory or should be some sort of gravitational theory, and that gives me ADS-CFT. So yes, the answer is yes, these are both valid descriptions of one and the same system, and they should be dual to each other.
Right.
And there are many more examples where you just study these extended objects in string theory, and very naturally you learn about new dualities from that by just looking at it sort of geometrically in string theory. So this is one of these instances where string theory, whether it's right or not, it has no. By right, I mean whether it's the correct description of quantum gravity in our world or not. It has definitely produced lots of very interesting ideas in that sense that it made dualities much more popular.
Yeah, exactly.
Then some of these dualities you can also describe without ever using string theory. So I think there's some people say, well, you didn't need string theory for this, but it's sort of come on, right? Yes, once you know what's correct, you don't know, you can do it otherwise. But these are, nobody would have, many of these advances people would have never found without having like string theory basically put it in their face and say, look at this got to be equivalent to each other. And then you can check it by other means.
So one would argue, like you mentioned, that dualities have been existing in physics for a long time. I mean, the most accessible duality that we found was obviously the light wave particle duality. What makes ADS-CFT duality so special?
Yeah, because it does give me a complete description of quantum gravity, right? Before we talked about string theory, I advertised to you, it gives me finite answer when I want to study gravitons of each other. So string theory is great when you wanted to study sort of quantum gravity at sort of this perturbative level where you have sort of flat space and you put some excitations on top of it. But non-perturbative string theory still sort of puzzlesome. So if I want to describe like changes to the geometry which are large, right, understanding, black holes in string theory can still be complicated. There's the ADS-CFT, so in this setting when my space-time is anti-de Sitter space, which unfortunately is not the universe we are living in, but it's sort of
That's true.
Similar to the universe we are living in, right? There's this thing people call dark energy, which is sort of this uniform energy density everywhere, but it's sort of a positive energy density everywhere, and that gives me sort of the Sitter space in the far future of our universe. if it were negative energy density everywhere, our universe would be anti-de Sitter space. And then sort of in anti-de Sitter space, I have this duality where I'm basically saying like all this complicated quantum gravity with put whatever you want to in there, like black holes and like all complicated objects that we think are complicated to describe, have this equivalent description in terms of like an ordinary gauge theory, the kind of thing physicists understand very well, that has like no puzzle associated to it, right? It doesn't have gravity in there. So this, you can use ADS-CFT, this duality, to basically say for like, at least when we put quantum gravity in anti-de Sitter space, there's like everything you want to know about it, we know in principle. Just go out there, calculate in the gauge theory, and that's the full answer. So it's, at some level, it's sort of the most complete, most beautiful description of a quantum sea of gravity that, you know, we are 100% sure. It's the ADS-CFT conjecture, right? It's, I think, no, a purist would go in there and say, you haven't proven it, but no, it's also established beyond reasonable doubt. Certainly at the level of a physicist, it's just true.
Max,
and it gives us a complete description of like a quantum sea of gravity.
Right. And on the other side of the duality, we have this quantum conformal field theory, right? How strong of a condition has to be on the boundary theory to be conformally invariant? Because we use ADS-CFT to study QCD, which is nowhere near conformally invariant. And how do these fundamental quarks and gluons emerge from in the bulk?
So conformal field series people would study even without ADS-CFT, right? Conformal field series have been very important in physics for a long time. For one, to describe systems near phase transitions. So that has lots of applications to real-world physics, because phase transitions are important in the real world. It's also, if you think about, what are all the quantum field series that I could write down, what are sort of the patterns in quantum field series? Now, quantum field series have this feature that the physics you see depends on like at what scale you're probing the theory, and then conformal field series are field series that do not change under scale transformations. They're scale invariant. So whenever you take any system that's described by quantum field theory that's not conformally invariant, you can kind of keep on scaling out and ask, as I go to longer and longer distance scales, if I look at like with a more and more macroscopic point of view, then eventually you land on a conformal field theory. It's sort of because if you keep on scaling, right, the system changes under scaling until it settles into a regime where it's sort of scale invariant. And so if you want to describe all quantum field theories, starting with all conformal quantum field theories would be a good start, because they're sort of the endpoints under RG evolution. And I can basically start with the other way around, start with the conformal field theory and then perturb it at something with a scale and kind of study sort of how things change as a function of scale. From the point of view of using ADS-CFT to model, say, QCD, where, as you correctly pointed out, QCD is not a scale invariant theory, right? I think it's not the conformal invariance that is the biggest obstacle. It's sort of not every conformal field theory has a nice gravity dual in ADS. It has to be very, very special conformal field theories that have a nice classical gravity description in terms of gravity, approximately classical gravity on some sort of large anti-de Sitter space. And yes, these are very special theories. And I don't think there's any real example out there where like a theory we genuinely care about to describe nature has a good ADS-CFT dual. The reason people do things like what you described anyway, right? So if you want to describe QCD, it's not conformal and it doesn't have a good gravity dual, and then you use gravity to describe QCD, right? What business do you have doing this, right? So I think this is sort of a tool people use in very special circumstances. There's some questions that are so hard in QCD that right now we have like no idea of how to even access them. Then ADS-CFT can provide for me some sort of laboratory where I can sort of explore qualitative questions, right? I should never expect to get like an accurate answer out of ADS-CFT because you're not you get accurate answers for the series which have an ADS dual. If you want to study n equals 4 super Young Mills, right, which is sort of series stream theory, that you can learn everything you want about n equals 4 super Young Mills by studying ADS-CFT. But that's not QCD, right? So you study n equals 4 super Young Mills and you just take this answer and you sort of transplant it to QCD. And that's sort of okay for questions where you don't know, where you just don't know what to do in QCD. You at least get sort of an estimate what should happen from ADS-CFT, right? Let me give you like one example that was like really popular like 15 years ago, which is sort of this, the viscosity of the quark gluon plasma, right? Sort of that's... QCD has this problem that is what I would call strongly coupled, right? It goes back to what we said before. We should write down QCD, the theory of the strong interactions. I write it in terms of quarks and gluons, but that's not what we see, right? And that's sort of a feature of theories which are strongly coupled, that the basic degrees of freedom they are using to write down your theory are not the things that you see actually in the experiment, right? Sort of the interactions are what dominates the theory. And then most of the techniques we have fail, right? Sort of when you learn quantum fields, you always start with like, there's this basic degrees of freedom. To begin with, I treat them as non-interacting, and then I slowly take into account sort of order by order and some sort of perturbative expansion. I take interactions into account. And that doesn't work if what you see in the end is completely different, right? You're not going to perturbatively turn quarks and gluons into protons and neutrons.
Right.
We do have good numerical techniques for QCD. You know, the mass of the proton people can calculate quite accurately in the computer using something that's called lattice QCD. But that doesn't work when you study time-dependent processes. You know, when they do lattice QCD, they have to do some trick where they basically treat time as an imaginary thing so that they can kind of, things don't wiggle, which they would as a function of time, but everything's sort of well-behaved and exponentially suppressed. So static properties of QCD you can understand quite well on a computer. But when you're talking about viscosity, that's sort of telling me like if two layers of a fluid sort of go past each other, how, if one is moving faster, one is moving slower, how does the faster drag the slower one along? It's one of the basic properties of any sort of fluid. And when you heat up QCD to very high temperatures so that the protons and neutrons break up into like a soup of quarks and gluons, that's sort of one of the basic descriptions of this fluid. Like one of the main quantities you would want to know about it is its viscosity. And that's about things moving. It's not a static quantity. So for this, people had like no idea what they should calculate. Right? They didn't even, they made some sort of rough estimates based on doing perturbations here at extremely high temperatures where the quarks and gluons are very free, and trying to extrapolate to the temperatures that we can actually realize when we kind of smash nuclei into each other. And those estimates were just way off. They had like they were making, before there's this, when people did this smash nuclei into each other, there were lots of people who said this will never create these fluids because we estimate things and this fluid should never be a good description. And just these were like very good fluids, behaved very differently from these estimates people gave from doing this perturbative calculation. And ADS CFT came in and did a calculation which gave something which is like within a factor of 2 agrees with experiment, right? And that is amazing, right?
Yeah.
It's sort of, and you can't do better, right? Sort of you can mess around with ADCFT and kind of dial around things a little bit, but you'll never get like a prediction for what the viscosity is of the QCD plasma doing ADCFT. But you get some sort of right order of magnitude estimate, and it comes with some sort of insights into mechanisms. You understand what's happening in strong coupling, right? Sort of how does the viscosity come about? It's sort of a strong coupling is sort of how these collective phenomena of like very many very like soft particles, so very low energy particles interacting very strongly with each other, how they can give rise to these sort of very low viscosities people see in the quark-gluon plasma.
Right. I mean, so there are two kinds of approaches that we use while studying QCD using ADS-CFT. One is the top-down and the bottom-up. How about you start by explaining the difference between the two, and how do we understand the fundamental degrees, which are the quarks and gluons, in both of them?
Yeah, so what I was describing to you was basically entirely top-down, right?
Yes,
I'm trained as a string theorist, and I like top-down because I know what I'm doing, right? So I'm calculating things in n equals 4 super-Young mills, where I have an exact reality. And the answers I get, right? I feel good if I do a calculation, I know it's right? There's a calculation, I learned something new about n equals 4 super-Young mills, there's an exact reality. And if you asked me, so Damson and his collaborators calculated viscosity, and then me and my collaborators at UW, we calculated sort of the energy loss of a projectile moving through this plasma. And that answer I trust to this day. That if you ask me, what's the energy loss rate of a projectile plowing through this n equals 4 plasma, I believe I know the answer. Right? But that, again, that's not QCD. People very much want to know the analog question of if you have like within this quark-gluon plasma, if there happens to be one of those quarks is much more energetic than the rest, it's kind of like a bullet going through this fluid. You want to know how does it lose energy? That's a question people really want to know. They sort of use our answers as a stand-in, and they're not exactly right. Yeah. But so this is top-down. You're starting with a theory where you have an exact reality, and it's not the right theory, but at least you get exact answers in this. And then you accept that this will be not QCD, but it maybe gives you order of magnitude estimates for QCD. Unravels the right mechanism, right? It's sort of a theory that's qualitatively similar to QCD. The mechanisms you see in strongly coupled Enickel's force to Young Mills at work are much more similar to the mechanisms that happen in strongly coupled QCD than you would, perturbative calculations would kind of predict. So bottom up is kind of, you give up on the idea of there being exact reality as you mock up some higher dimensional theory of gravity, which you engineer in such a way that it kind of reproduces the properties of QCD, right? Sort of that has its place, right? I think it's not a theoretically well-defined framework, right? You can always, like, if you don't like the answers you get, you dial a few more dials in the bulk, you add a few more degrees of freedom, you can get pretty much any answer you want by just engineering the 5D bulk. But these models are quite if you kind of focus on like simple models, right, you can kind of capture the properties, model the properties of QCD by very simple 5D models. And then it's sort of, if you want to do quick and dirty estimates of what happens, they're like so easy to calculate, right? I heard you're working on this, right? So this is sort of, I think people do this because it's like when sort of for first guess, right? If you want to study some new process, it's sort of probably the easiest way of calculating anything. Bottom up, you still have to solve Einstein's equations. No, you can't just give it to a high school person and say, do this for me, but it does still require quite a bit of skills, but it's much, much easier than the things people do if they want to do like honest field theory calculations, or if they want to know. Even top down is probably harder, and then you're studying the wrong theory to begin with. So it's sort of I would think of them as toy models, which give me like quick and dirty estimates, and they're tuned to kind of reproduce essential features of QCD.
Right. So you mentioned that all ADS-CFT can do is provide you like qualitative answers, build toy models to answer these questions. My question is...
they give me exact answers for Enickel's force of Young Mills, but the qualitative answers for like...
For QCD, I mean. Yeah. I should be careful. You're absolutely right. But the question is, because we know QCD is strongly coupled, what are some other candidates? So what do we do now? So we know that we can only get, using dualities, we can only get qualitative answers.
So now what people have been doing in the ADS-CFT community, they've been hunting problems like this, right? It's sort of ADS-CFT is sort of, if you want to use it as a tool to do physics in other areas, right? It's not like a cure-all, but you want to find problems where people are confused at such a basic level that getting qualitative answers is actually a good thing.
Can make progress.
Yeah, and then people move on, right? This ADS QCD, so where people use ADS to study QCD, was a huge thing for a while, and then people just sort of dropped it because a few people stayed behind and kind of now solve the hard problems, but it's sort of right. ADS-CFTs, I think, is a very good tool when you want to kind of, when you're confused at a very basic level, just want to get your bearings straight, identify the basic mechanisms, get order of magnitude estimates, and then it ran out, right? Sort of, it's not like if you work harder, you can do better. It's sort of, it keeps on describing Enickel's force of Young Mills no matter how hard you try. So then people moved on, describe superconductors. I think they're like new transport phenomena that have been developed and have been discovered using ADS-CFT, right? People keep on doing this. ADS-CFT is a great tool whenever you want to discover some new basic phenomenon, when there's some area of physics that you identified where the problem is so hard that qualitative answers are useful, but then it runs out.
I see. Nice. So for the next part of the discussion, let's actually circle back to string theory. And as we've been discussing, that the theory itself opens up Pandora's box of sort of concepts and possibilities. You mentioned extended objects, extra dimensions, different ways to compactify these extra dimensions, and so on and so forth. And that naturally overwhelms the community to sort of construct theories of the physical world. And what I'm alluding to is the landscape and the Swampland program. So do you mind telling us what that is and what is its current status?
Okay. So I haven't really worked actively on this myself, but it's a big fraction of my field, right? It's right now this study of like the landscape versus the Swampland. And if you just write down field theories or classical theories, right, you have a lot of freedom. You can write down sort of arbitrary Lagrangians. So this is sort of the way how we describe a basic theory. Sort of the Lagrangian is an object that encodes how things talk to each other, how the basic degrees of freedom interact with each other. And they have three parameters, and they're completely unconstrained, basically, from the point of view of just writing down sort of what I would call an effective field theory, right? Sort of the low energy description describes our world.
Mm-hmm.
And in string theory, we have all these options, right? All these extra dimensions. They have lots of different shapes, and you might think like pretty much anything goes. And this landscape where there's Swampland is trying to quantify this, where they say, string theory, it's true that we get like this infinite, don't know if it's infinite, but very large number of like possible low energy descriptions. But the claim is it's still not really everything goes. So if you're just starting from like quantum field theory, classical gravity, there seem to be lots of things that make sense as a field theory that cannot be embedded in string theory. So this discussion of the landscape, whether the Swampland would be trying to find some sort of what set of possible field theories that you could write down, low energy field theories, do not make sense within string theory. So you would say that even though they make sense as a field theory, if you try to kind of bring in quantum gravity, those theories can never ever be embedded in a consistent quantum theory of gravity. So it's trying to find, right? You have two very large sets, the like set of all low energy field theories you could write down, and the set of all things that come out of string theory. But the claim is there's like string theory can do almost everything, but not quite everything, right?
Okay.
Almost everything goes in string theory. That's the landscape, and then the Swampland would be the things that look consistent as a effective quantum field theory, but they don't come out of string theory.
Right.
And sort of, this program as a whole, it actually has accomplished way more than I thought it would ever be possible. Because to me, when people tell this to you, it always sounds like who cares, right? You're still left with like this, basically infinite number of possibilities. But the sort of ideas people developed on the way, I think they were very helpful in us trying to understand some sort of basic principles. If you study sort of what can possibly happen in string theory, people find that like the things that are living in the landscape. So the landscape is what can happen in string theory. The Swampland is what can't happen in string theory.
Right.
The things that are living in the landscape obey some sort of very generic scaling properties. If you go sort of to the corners of moduli space is the space of all the things that can happen in string theory. If you go sort of the corners of moduli space, there are some very generic patterns of like how masses of states behave near the corners of moduli space. It's sort of people had sort of been aware of on an example by example basis, but I think people found new ways of organizing their thoughts on how to think of sort of the space of all possibilities once they ask questions in that way, where they ask sort of, how can I find that boundary between what's possible within string theory and what just isn't possible within
So the Swampland program, does it just help us to organize our quantum field theory or theories of quantum gravity, or does it provide some constraints?
I think the sort of the way people would advertise it to you is sort of it gives you experimental test of string theory, because if you measure that we are living in the Swampland, you would have ruled out string theory. But no, for a believer who thinks that string theory is the right description of the universe, so I would be very surprised if somebody finds you're living in the Swampland. If just knowing that we're living in the landscape, we're back to saying, well, the landscape is huge, right? Almost everything goes within string theory. If just I know that I'm living somewhere in the landscape, it doesn't really help me kind of understanding sort of these corners of the landscape. But no, it did help, I think, people understand a little better of kind of what, organizing their thoughts about sort of what this landscape actually looks like, especially sort of what the corners of the landscape are. I think this helps. Right. Ideally, you want to write down the strings you described, right? You don't need the entire landscape. There's like one point in the landscape, and that's the right one. But sort of by understanding how the landscape looks like, maybe this will help a little bit understanding better of sort of, what would be the criterion that eventually tells me that special point in the middle of the landscape at which we're actually sitting. I don't think we got any closer to this, right? People learned a lot about string theory using this sort of Swampland program, but I don't think it got us any closer to kind of experimentally verifying that string theory is the right theory of everything. Right? It gave us some in principle ways of ruling it out, and it hasn't been ruled out yet.
Right. And probably we won't be able to find that one particular theory of quantum gravity that perfectly reproduces the
I would hope eventually it will. I'm not very optimistic it will happen in my lifetime. I know I don't see a near-term path to where we'll find the correct string theory. But the only way to make sure that we'll never find it is giving up. I think it's still a very... we should still train people in understanding string theory. String theory constantly makes progress. It's just... we shouldn't pretend that we're 5 years from now I'll tell you like string theory will describe like the universe for sure. I don't see a near-term path there, but I still think it's like our most promising route to unifying quantum mechanics and gravity. And by all means, we need to kind of pushing the frontier.
Yeah.
Brilliant.
Yeah, very exciting thing I read about. This was from Wafa's work that because of the smallness of the cosmological constant, we get to one of these corners. And then there's like this relationship between dark energy, which is small, and then you get tower of particles.
Yeah.
You get
So
some
some
power law
people
hierarchy. Of,
Sorry, yeah.
Go ahead. Yeah.
So some people try to use the landscape program to kind of come up with new phenomenological models. Right? This is one idea that people can, right? Where he even tried to push it to the limit, where he kind of tries to come up with a new model that one can test out of that Swampland program. But I don't think it would be like a prediction that this is what string theory has to do. It's just like a new interesting corner of string theory that can be explored. Right? There are few corners of string theory where you could get lucky. Right? There's this. My local colleague Vadim and Elena Caceres a long time ago, and then later Akani Hamed and his collaborators explored these like large extra dimensions. Right? If these extra dimensions were really, really big, we might see them like any day now. Right? It's not like string theory predicts that they have to be big, but no, if nature were kind to us and just kind of happens to live in the corner of the landscape where it makes it easy to detect these extra effects, we could see it.
Right.
It's just there's no like. I think nobody can kind of really make a strongly convincing argument that they have a prediction that we have to live in one of these easy to find corners. But there are corners of the string theory landscape that would be nice. That would make it possible to find string theory in my lifetime. But again, I'm not super optimistic. It's not something we can do, right? It's sort of nature would have to be like this, that it just happens to live in a corner of the landscape that happens to be easy to find experimentally.
Fair enough. So I think we're a good point at talking about stuff that you have been doing. So Brane models and its application to holography. So can you talk about, I know you talked about branes a little bit, talk about what these objects are and how this approach is different from what we currently have.
Yeah, so these branes that sort of Lisa Randall and I worked on like 20 years ago and that became popular again reasonably, they happen to be branes that we don't know how to get out of string theory. So they're part of this sort of bottom-up world.
I see.
Where we kind of, there are things that you can construct in string theory, very complicated geometry, whose features are similar to those we can get from these bottom-up branes. There's been some very famous work by like Lisa Randall and Raman Sundram, the Randall-Sundram brane worlds, where they came up with sort of phenomenological models of how our world could be like, where we would be living sort of on a 3 plus 1 dimensional brane. So our universe has 3 space, 1 time direction. So our 4D universe would be living in some 5-dimensional strongly curved space. And they discovered, which was a real surprise to people, which is something people should have known decades ago. It's a classical gravity phenomenon that if you have these branes in these strongly warped, strongly curved, higher dimensional spacetimes, that they can trap massless 4D gravity, like ordinary 4D gravity on this brane, even so the universe is 5-dimensional.
Right.
And that gave people a completely new way of thinking about higher dimensional models, what could be beyond the physics we explored. And one very nice feature is because of the strongly curved 5-dimensional geometry, energy scales get translated into position in this higher dimension. Where things are located in the higher dimension corresponds to sort of what energy scales they're happening. So there are many times in physics where people wonder why are there like the basic scales of the underlying theory that the standard model that works, that describes physics as we know it. There's a bunch of puzzles of where like things happen at different scales, where you kind of, why is this happening, right? It's sort of, whether this is a real problem or not, people debating all the time about, but at least it's sort of, if you want to write down theories of like that maybe go beyond the standard model, sort of certainly getting these large separations of scales is always something you have to, that appears puzzling.
Right.
It's kind of, you have to do some kind of dirty manipulations to get this, and in these Randall-Sundram brane worlds, that's very natural. It's just kind of you put things at different places in the 5-dimensional bulk, and then you naturally get like can get very large hierarchies between different scales.
I see.
That's sort of these are the two things that made them very appealing. And then sort of Lisa and I explored what happens if you basically take these brane worlds and make the brane itself be an anti-de Sitter space. So at the moment you do this, you kind of again, this is back to ADS. It's sort of the serious, most favorite spacetime because it's easy to deal with. Sort of the moment you go to ADS, you're leaving the real world behind, right? We are definitely not in ADS, right? I think we know that. But sort of these models that Lisa and I then wrote down, they within this framework of ADS CFT, you can do very interesting new things with them. Sort of they became recently more popular again in kind of the context of people trying to think about black holes and how they evaporate.
Okay.
It's actually quite roundabout of why they might be somewhat important there. It's sort of people like, if you're an ADS, black holes can actually live forever. Right? Black holes in the real world, they'll eventually die, right? Black holes, as we know them right now, they only get bigger because they gobble up all the stars around them. But sometimes they're done gobbling up because they've eaten everything they can. And then Hawking tells us once you have like these black holes and they stop gobbling, they have actually finite temperature and slowly radiate things off. And eventually, like long after we are all dead, black holes will start evaporating and disappearing, right? It's like very, 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 very distant future. But black holes in principle can disappear, but in ADS, because ADS ends up having acting like a box, it has some boundary that kind of makes sort of these black holes try to evaporating. Eventually this radiation that they're emitting reflects back and gets back into the black holes. And so if black holes in ADS can actually live forever, but then if you kind of put them on a Brane and have it interact with some external bass, they can evaporate again. So it's like an exception to an exception to an exception. But it's sort of, theoretically, it's kind of one of the simplest places in which you can have sort of study black hole evaporation in a controlled setting. And therefore, it's been like one of the tools people have been using to kind of try to understand the physics of black holes.
I see. So, well, as theoretical physicists, it is often hard to make realistic contact with experiment. And I know you're thinking about it, and you also mentioned that, this is how people advertise their things now. So what are some of the experiments that you're actually looking forward to, or like you think can make contact with quantum gravity?
I've been in this field now for 30 years, and so far I have not made a single experimental prediction. That's sort of it is an embarrassment, and I hope before I retire I can make contact to at least one experiment. But I mean, cosmology is probably like, if you're talking about understanding quantum gravity, that's probably like right now the forefront where lots of new data is coming in. And
right.
There's a very pessimistic outlook, right? If what we call dark energy is what we would call a cosmological constant, so this is truly this constant energy density everywhere. We may not learn much about fundamental gravity from all this cosmology, but maybe it's not, right? There's recent hint that maybe dark energy is evolving, and that sort of would be so much more exciting. Although I think the Swampland people would really like it. They want to say sort of constant dark energies are sort of bad, but sort of we might be up for surprises, right? Whenever you explore physics that hasn't been explored, there's always the hope that we find something that will teach us something genuinely new. But in principle, new particle accelerators could teach us something new, right? It's sort of, if somebody were to build a machine which has like 10 times as much energy as the LHC, that could teach us something really new, right? I think there are lots of people that is not really. Many people think that this is not good enough motivation for investing the kind of money that's required for a new accelerator, right? But no, I can't guarantee you that just crank up the energy by a factor of 10, will you definitely learn something new?
Maybe not.
No, all right. It's like our only way of going there, right? Sort of, I think it would be very interesting to do, but it's sort of, one can ask that question. I think it's sort of a valid point to wonder whether it's the most efficient use of resources.
I see.
But I would think cosmology is probably our best bet right now, where we might see like a sudden surprise that maybe I'm too pessimistic about like how long it will take. Maybe cosmology will surprise us in a good way.
What about some low energy tabletop like experiments, or like even in the quantum computing world?
There's a lot of noise about, we can test quantum gravity in the lab by using sort of ideas from ADS CFT, where you have sort of some simple lower dimension versions of ADS CFT, where some quantum mechanical system that you can actually realize in the lab might be dual to some lower dimensional theory of quantum gravity. I think this is very exciting, but I don't think it will teach us about quantum gravity, because usually in these cases we understand why 2D quantum gravity people basically solved. So these are all systems where, like on the gravity side, people kind of know the answer, and the interesting phenomena happening in the quantum mechanics, right? Gravity tells you that like these systems which have like good gravity tools, they sometimes have very interesting properties as a many-body system, right? They kind of have this, they're fast scrambling, so they kind of distribute information about all, you put information in a few degrees of freedom, they distribute them across the entire system very fast, much more rapidly than we would be used from sort of weakly coupled systems. So they have some very interesting properties as many-body systems, which sort of gravity motivates, and we should test that and kind of know, maybe it will teach us something new about sort of quantum information problems. How does information spread in systems? Sort of what are good ways to probe them? Maybe new ways of thinking about how to build quantum computers.
Right.
But I'm not very optimistic they'll teach us something new about quantum gravity. Because again, in the cases where people do this, it's usually where we understand the gravity side already.
Right.
We use the gravity side to make all these predictions about what the quantum computer should see. So I think it's exciting as sort of pushing our frontiers of what we can do on sort of the technical level in manipulating these low dimensional systems of many atoms talking to each other. But I would not. I think people who advertise this as a way of testing quantum gravity, they're really probably, they're kind of not being entirely honest with the public. I feel like this is exaggerated claims that you could learn about quantum gravity that way.
That makes sense. Yeah, absolutely.
The SYK model, in fact, is one of the models which has a 2D dual gravity. Do you think that
sort
is
of
also
right?
a
I would
model?
even say that's sort of exaggerated.
Yeah.
Sort of the very low energy sector of the SYK model has a gravity description, but the full SYK model I don't think we have a good gravity description for. The SYK model is a very important body system. It's kind of, it's a paradigm for what happens in strong coupling, right? It might help us understand high temperature superconductors, right? Sort of I feel this is sort of definitely the gravity community and the people who study strongly coupled systems for other reasons can interact with each other very fruitfully, right? Things are easy to calculate on the gravity side. You might learn new qualitative lessons about an SYK, which then, by now you probably don't even need gravity anymore. People kind of find all these things that people study, use gravity to find, to kind of directly see in the SYK. Sort of, it's definitely the crosstalk is helpful. I just don't think it will teach us something new about quantum gravity.
Right.
But I think this is very exciting research to do, and it's definitely worthwhile continuing and pushing further, mostly because what it will tell us about like how information spreads, how strongly coupled systems behave. High TC superconductivity is like one of these puzzles that people like to understand for decades and still don't. If that sort of thinking can help us there, that would be great.
I see. Yeah, and all of that has been enabled by ADS CFT, so this should be enough evidence.
Okay, I think so the S of SYK super such stuff, he wrote his SYK model down before he did ADS-CFT, but he now joined the crowd, right? I don't think you needed ADS-CFT, but it certainly has helped, especially I think this crosstalk where people who kind of do ADS talk to people who do like condensed matter physics, strongly coupled systems. One definitely approaches problems from a very different point of view and learns a lot from each other by talking to each other.
Right.
Interesting.
Now, touching a little bit on philosophy, does string theory hint at or perhaps prefer a particular interpretation of quantum mechanics, or is it just agnostic?
I don't think we would learn from string theory about interpretations of quantum mechanics. Whereas string theory is like you start with studying these little objects using quantum mechanics, and sort of you basically have to already have settled of kind of what you mean by quantum mechanics.
But like, do you personally have?
I think there are very few working physicists who worry too deeply about the foundations of quantum mechanics. Right? There's this. I would call this, like, people used to call this, and I would subscribe to this, shut up and calculate approach.
Okay.
So there's like we have no problem calculating with like quantum mechanics without worrying kind of like who's an observer, who's not an observer. If you talk to Scott Aronson in our computer science department, right, sort of the people who do quantum information, they kind of have more to say about this. But it becomes a little bit like in this recent discussion about observers in quantum gravity, it actually becomes a little bit more of an issue of kind of how to in quantum gravity, we sometimes have a hard time even pinning down what are good things to calculate, what are right observers. And then
right.
There's like a few recent papers who kind of suggest that you have to seriously think about actually the observer as being part of the system to kind of make sense of what are actually the right observers in quantum gravity.
Interesting.
But this is still a little different from thinking about sort of this interpretation of quantum mechanics. I think people would still kind of more or less ignore that.
Especially in this community, or like, do you spend some time thinking about it? Just amuse, with in your free
It's
time.
fun talking about it, right?
Okay,
It's fun
okay.
talking about it. I don't see it impacting sort of what we do on a practical level.
Okay.
It's sort of what I'm calculating is what I'm calculating. I know how to calculate scattering amplitudes in quantum mechanics. I know how to calculate probabilities in quantum mechanics without worrying too deeply about who is that person who would actually see that and kind of are these like, did I just describe many worlds, or is this somehow it doesn't make a difference to me, right? It doesn't make a difference to
That's
what
fair.
I do.
Fair enough.
That's fair. Okay, so moving on to the tail end of the podcast, it's always good to understand and helps young researchers. How did you get interested in physics? And let's take that trip down the memory lane.
High school
High
teacher.
school?
Yeah, it's like I could pinpoint one teacher in high school who was not. I
knew
knew I
so
wanted
teacher
to.
made a difference.
One teacher, yeah.
Awesome.
I knew
That's awesome.
it's like math or physics or something this general area, but and I probably was more towards math. But I had like one physics teacher. So back when I went to high school in Germany, in the last 2 years of high school, you have to specialize on 2 topics, where you kind of it's like majoring basically, but sort of not quite as specialized as in university, but you have to kind of pick 2 subjects that are like your main focus. And I picked math and physics, and sort of that physics teacher I had for 2 years in that course made a huge difference in me deciding that physics is it. That's where I'm going.
That's awesome. That's very nice. So it was like the 2 years spending time with him, or like did you meet him outside of school?
No. I mean, it's mostly the way he taught physics, right? I mean, you could say in the end it was the material, but I think he presented the material in a way that I found. He's probably not even like sort of super engaging. He just was good. I think he taught me. He was a good teacher. Did a good job teaching me physics, and I enjoyed it and fostered my interest in that.
That's fantastic.
And finally, what do you feel we, and especially young physicists who are just starting the field, how should they look at string theory today?
No, I think you should know about it. No, you should. Maybe one thing before you want to strongly express your opinions about it, you should probably know about it. No, you can have a happy career in physics without actually being deeply involved in string theory, right? I feel like we should train people and keep on doing string theory, because I don't see a viable alternative to it out there on the horizon, and just ignoring quantizing gravity shouldn't be an option, right? We shouldn't be happy with saying this is sort of a problem we refuse to tackle, especially if there's a candidate who can do it.
Right.
But before choosing it as a career, I would be very wary, right? There are fewer jobs now in string theory there were when I got hired, and I think for a good reason. I feel like we have to continue doing this, but it's definitely not the most employable career options out there. I think physics is a very valuable training. If you get a PhD in physics, it's a very good degree to have to be competitive on the job market. Especially if you shouldn't get a physics PhD to stay in academia, right? Most people with a physics PhD don't stay in academia, but it's sort of, if you want to stay in academia, probably string theory is kind of one of the hardest paths to choose. So
because it's inherently hard, or like just because
it's still despite all this bad press it gets, it's still a very attractive.
Right.
It still holds young people who go into theoretical physics, they still kind of do it for dreaming of solving these big questions. And there's still a lot of people who very much like to go into string theory to start understand black holes in the early universe and how to quantize gravity. And there are much fewer jobs now. So I think and it is a very hard field. So it attracts very skilled people. So there are lots of, the competition is tough in the sense there are lots of other people out there who kind of did really well in physics, so the entire career. And they won't all get a job in academia as a string theorist, right? I still think in the end you should follow your passion if there's something you want to do. Right. I'm just not. I'm a little frustrated with people who have very strong opinions about string theory and have no idea what they're talking about. So I think if it's
You're absolutely right. Yeah, they should know what it is before saying.
So so I think as a young person who's interested in physics, either stay out of it or at least be informed before you try to comment on it. And I mean, it's fine to ask questions and kind of even ask critical questions, but don't kind of think you have figured it all out and know so much better than the people who invested their lives, careers into understanding it.
So, like, for example, you said that it's in terms of employment, it's not the most wise choice to do string theory, at least right now. Have you seen examples of people transitioning out definitely, because funding obviously dictates what people are doing, but have you seen people transition into string theory from other fields? And when it picks up, people have sort of come in and then started doing things, and they've come up with different ideas from other places in physics and helped.
I mean, there are lots of people who do string theory as part of what they're doing, right? There are people from quantum information who kind of see the ideas having impact in string theory, come in and want to do a little bit of it. There's people from the condensed matter world who see like AD/CFT being interesting and then kind of dabble a little bit in string theory.
Right.
I think there's few students who like as undergrad did something different, which I think doing string theory as an undergrad is kind of almost impossible to have like an impact, right? I always, when undergrads come to me and say, can I work with you? I say, do something else first, right? Learn how to do research, do something where as an undergrad you can actually have an impact. If you really, really, really want to do string theory, come back to us as a graduate student. So I see people early on in their careers shifting over, but I think it's hard to kind of see somebody who's done something completely different and then right now would come into string theory and then have a major impact. I think would be
difficult,
unwise move, right? But no, picking up string theory as something that you do as part of your portfolio, that's definitely right. As I advertised before, this crosstalk between string theory and other areas of physics, I think, has been very fruitful for both sides talking. But I think most people kind of are very happy with having like expertise in something that's other than string theory and then doing string theory on top of it rather than completely switching over.
Right.
I see.
Okay.
I see. Well, Professor Karch, that was it for today. Thank you for doing this. It was a pleasure having you on the Knowmads podcast.
Yeah, thanks for coming all the way to Austin to talk to me.
Thanks very much.